We're on page 81 of the notes. We're going to talk about one-sided limits. So again, today's idea is really not too hard, especially if you've understood 2.2. This course, I will say, it is imperative that you're keeping up with the homework and mastering it between classes because it continues to build. If you take 2-3 days off of homework, you're going to really start feeling pretty much like you're drowning. So make sure that if you're feeling like you're drowning, do that 1 or 2 steps that you have in your mind to go ahead and get back on top of things. But we're going to learn about one-sided limits today. We've already talked about this expression right here. The limit as x approaches c of f of x is called a two-sided limit. And we kind of saw that earlier because we would approach it from both sides, and you would see I'd kind of do an arrow on both sides of whatever we're looking at. We will now investigate one-sided limits, and we're going to consider this function right here. So this function is graphed for us right here. Well, what we've already talked about is the limit as x approaches 0 of x over the absolute value of x. Well, of course, if you don't have the graph, the first thing you should always try to do and evaluate the limit is what? Plug it in. Notice again, if you do 0 over 0, does anyone remember what type of form that's called if you get 0 over 0? Indeterminate. I heard a few of you out there. Very good. So this is an indeterminate form if you just try plugging it in. So that doesn't work. So we're going to learn some techniques to approach it today, but we're going to just use the graphical representation. If you recall, as we approach 0 from the right-hand side, you see when we look at the graph, we're approaching 1. If we approach 0 from the left-hand side, you can see when we look at the graph, we're approaching -1. So because these are different, what we would just simply say before is that we would say the limit as x approaches 0 of x over the absolute value of x does not exist. Or in short, we would say DNE or DNE. But if you think about this, what I just did is I just said, okay, as x approaches 0, and this time I'm going to kind of write it here from the right, what we can go ahead and do is translate to the graph, and we see the limit there was the y value 1. So right there in red, what we have is the limit as x approaches 0, and then to indicate I'm only looking at it from the right, I would use this little addition sign on the zero, that superscript. And for some of you who remember this from pre-calc or have been remember kind of the rational functions chapter, is that same notation that we looked at when we were first learning about rational functions. Of course, we still consider the limit of a certain function, but this time we would say that the limit is equal to 1. And then the thought process could handle and be similar, that if you approach it x equal to 0 from the left this time, from the left, you'll see the limit as x approaches 0. Does anyone want to take a stab at what I'm going to put on top of the 0 here? A negative. Glad you're following that. We'll just have the limit as x approaches 0, and that negative is read from the left, and it would be equal to -1. So that is the idea of one-sided limits. Any questions on this first example? Okay, awesome. One thing that I want you to go ahead and grab right now is notice that the one-sided limits differ. Notice that the one-sided limits differ. And because the one-sided limits differ, that's when we would lead to this idea that the two-sided limit does not exist. I'll say that again, and we'll explore that in various other examples. When the one-sided limits differ, the two-sided limit does not exist. What we have right down here are a few sentences that rehash what we just said above. We had the right-hand limit, L at c, and we simply wrote the limit as x approached some value c from the right, indicated by that little positive sign, and then we still have some function. And again, there's that symbol that we use to represent it. And in this case, we only consider values of x that are larger than c. And we'll look at that, what that means algebraically here in an example in a few pages. We also looked at the left-hand limit. Again, m, it doesn't matter. They just wanted to use a different letter. So this could be like L2 if you wanted to, whatever. Then we write the limit as x approaches c from the left, indicated by that little negative sign, and we saw that above. And in this case, we only consider values of x that are smaller than c. So that'll help us out algebraically simplify things, and we'll see an example in a few pages. The good news is that all two-sided limit laws apply to one-sided limits. So guess what? If we look at this example right here, we're on number 1, where we're asked to find the limit as x approaches 1 from the positive, or right-hand side of this square root function. To find this limit, what do you think we're going to try first? Plug it in. So what we'll have to do is just, let's see if it works. We get the square root of 1 minus 1 over 1 plus 2, which is going to be the square root of 0 plus 3, over 3, which is the square root of 0, which is ultimately 0. The limit here is 0. Just to clarify something, let's say we had 1b, and we have the limit as x approaches 1, this time from the negative side of the square root of x minus 1 over x plus 2. Anyone think they know what the limit will be here? I hear some of you saying yes. 0, 0. Yes. Yes, you're right. That was not a trick question. You're still going to try to plug it in. It doesn't matter if it's from the left or the right. And just to clarify, what are we going to plug in? Positive 1 or negative 1? That's maybe where the trick was, and I wanted to clarify. We want to plug in positive 1. That negative, it just means it's from the left. We're still approaching 1. We're approaching, or we're near positive 1. So you're still going to just plug in 1, and then you'll still do minus 1 over, again, 1 plus 2, which is ultimately going to be the square root of 0, or 0 just like above. So again, that superscript is just indicating the side of the x you're approaching. Any questions on that first example? Awesome. So go ahead and take a look at this second one right here. First thing I should do is try plugging it in. But when I plug it in, what do I get? 0 over 0. So kind of the same idea before. That's indeterminate form. We'll be able to use that later. That'll be section 4. This will be useful in section 4. I think it's 4.5, but we're still in chapter 2. So we'll use that indeterminate form later in section 4.5. So what did we do if we can't just plug it in? What should we try to do at that point? Does anyone remember this fact? Factor and cancel. So if you look at this, what I'll do is I'll just factor out that x in the numerator. So notice I am still writing the limit because I'm not plugging in anything here. I'm just factoring out an x, leaving me with an x squared minus 2 over this x in the denominator. So we have a cancellation of those two x's. So good. The limit as x approaches 0 from the left-hand side of x squared minus 2. Now we can go ahead and plug it in. And what do we find the limit to be? The limit here is simply going to be 0 squared minus 2. And as I heard many of you say, minus 2. Very good. So there's the kind of those two base examples for limits. Try plugging it in. If it doesn't work, try factoring and canceling. If those methods don't work, we're going to look at another way of dealing with the trig functions later in this lesson, but all of those rules still hold. You could take the sum of the limits, you could take the quotient of the limits, etc., etc. Any questions on these first two examples? Then let's move right along. There is one little subtlety we want to be careful when it comes to working with one-sided limits, and that's when we have to consider the domain. So when we talk about one-sided limits, they are related to limits at the interior points. So again, this will show up a lot more in chapter 4 as the interior versus the boundary points. So we're just beginning to get used to working with the differences here. So theorem 6, we actually already stated a function f of x has a limit has a limit as x approaches c. So notice that this first statement right here is talking about a two-sided limit because it's not specifying one side from the other. If and only if it has a left hand and a right hand limit, so and a right hand limit, and these one-sided limits are equal. So we kind of said this on the first page, kind of the inverse of this, I should say. We said that if the limits differ, then the two-sided limit does not exist. This is saying if the one-sided limits are the same, then we know immediately the two-sided limit. But we do need to be careful about that one. We'll see a question later that'll allow us to think about it. So, this statement, at a blank point in the domain, a function has a limit when it has an appropriate one-sided limit. So this blank right here should be boundary. At a boundary point of the domain, the function has a limit when its appropriate one-sided limit exists. And we'll talk about what that means here in a moment. So consider this circle or semicircle right here. What is the domain of this function right here? I hear you out there, -2 to 2. Very good. If I ever pose a question, feel free to answer it. It gives me a moment to breathe. The boundary points are the ends of the end of the domain. So the boundary points are x equal to -2 and x equal to +2. So it's just over here is a boundary point and over there is the other boundary point. So now we're asked a series of questions about the limit. So on this first one, we're approaching 0 from the left-hand side. So again, I'm going to be approaching it from the negatives. That's the x value I'm approaching. I translate that up to the graph. And again, this is a semicircle with radius 2. So what would be the limit for 3c? It would be a +2 because again, this is a semicircle with radius 2. So that right there is the y value 2. Now this right here, on D, we're approaching 0 from the positive or from the right-hand side. So what is the limit in the case of D? It is also 2. Very good. If you look at these two values right here, +2 and -2, they are equal. So because these are equal, we can say that the two-sided limit, the limit as x approaches 0, is also equal to 2. And really, we would have been comfortable with that with our thoughts from back in section 2.2, where we would have just said, oh, look, we're pointing to the same y value, namely 2. But again, that just shows to say this is the notation and the thought process is broken down using this superscript notation. Any questions on C, D, or E? Yeah, question.
It would have made a difference if there was like a hole at x equals 0.
Correct. So if there was a hole here, it would not make a difference because the limits are about what's happening near, what's it approaching, not what's actually happening there. So even if this was like up here at 3, the limit would still be 2. Is that what you were asking? Great. Okay. F, on the other hand, if we look at this one, we're looking at the limit as x approaches 2 from the right-hand side. So if we look at this right here, what we're trying to do is approach it. Let me kind of circle it over here in purple. That's the part of the graph that I'm looking at. If I'm trying to approach 2 from the right-hand side, was there any graph to even jump onto there? No. Everything greater than 2 is not part of the domain. So this is the case where the one-sided limit does not exist. There's just, maybe I'll put it in parentheses because x greater than 2 is not in the domain. But if you were to go ahead and consider x as it approaches 2 from the left-hand side, you can see I'm approaching 2 from the left-hand side. I translate that up to the graph. What y value is that this arrow approaching? Right here, which is 0. So this is 0 because, again, I take this arrow, I'm approaching 2 from the left. I translate that arrow to the graph and look at what y value I'm approaching. The y value I'm approaching is 0. Any questions on F or G? Now, this is what this statement was talking about right up here. Let me kind of make the connection. Let's just do it in like a gray. So this statement is talking about H. At a boundary point of the function, 2 is a boundary point, a function has a limit when it's appropriate one-sided limit, when it has an appropriate one-sided limit. So notice that this one is also going to be 0 because I'll just kind of translate it down here, because the appropriate, which in this case would be the one that's part of the domain, one-sided limit exists. And the appropriate one in this case is the left hand limit. So there's that little bit of subtlety when it comes to the notation. If you are at a boundary point, you can still have a two-sided limit notationally, but it's just because you're not thinking about anything that's not in the domain. So anyone have any questions about H, and everyone okay with why that's 0 despite the two one-sided limits being different? And it's because we're at a boundary point. All right, so on the next page, let's go ahead and see what we have there. We have example 4, which is just a little bit more of a piecewise example to go ahead and put together. You know, we got to find our proverbs right here, all the wisdom and piecewise. Okay, that is such a stretch. I'm not even going to try it anymore. 4, consider this function f in the following graph and determine the following limits. So let's do these first 3 together, just to make sure you got the idea. The limit as x approaches 0 from the right-hand side, from the positive side. So here, what is the answer to A? Now that I kind of have the thought process drawn up there, it is 1. Very good. So this is 1. So now when we approach 0 from the left-hand side, we see this happening. What is the answer to B? The answer to B is that the limit does not exist because, again, notice the domain does not include the negative values. So this is just simply does not exist. So what this means, again, maybe just let me call this out. X equal to 0 is a boundary point. So with that being said, what is the answer to C? Anyone? It is going to be 1 because the appropriate one-sided limit exists. So even though these differ, it is still okay because, maybe I'll draw the connection from here to here, I should, because the appropriate one-sided limit exists. But when we look at, when we look at D, well, I guess D, we're approaching it from the positive side. So as we approach from the positive side right here, what is the answer to D? It is also 1, because as we approach 1 from the positive or the right-hand side, we translate the arrow to the graph, and we see we're pointing at the y value of 1. What about E? When we consider the limit as x approaches 1 from the left-hand side, we're looking from here, and we're looking at here. What is the limit when we consider the left-hand side? 0. Because these differ, what do we say about the limit For f, we simply say the limit does not exist. Good. I think the majority of us are seeing what's happening. Any questions on those first 6? All right. Now that we've settled in, let's see what we got here. Go ahead and take about 1.5 minutes to 2 minutes and go ahead and answer G through O. Okay, I really am tempted to say some sort of go joke. Get it? G through O? Anyway, we'll just go with it. And go ahead and read through number 5 and think through 5. So let me give you about 1.5 minutes, 2 minutes, finish G through O, and also think about number 5 for a moment. I'm going to take attendance. I'm going to go ahead and start silently putting up the answers so you can check your work. So here are the answers for G through O. Raul, this one illustrates your point, right, or the question you had earlier. So hopefully that you did well on that one. The M through O is another example of what we saw in A through C. And G through I is a example. Well, actually, this is the example, Raul, that you asked about with the one-sided limits and the point. This one is just your standard limit right there. So there's that. Does anyone have any questions about the ones that I asked you to try right there? Yeah, Jason.
Just go over M really quick.
M?
Yeah.
Sure. So in the case of M, we're considering 4 right here, and we're approaching it from the positive side. So that's the x-axis. And to find the limit, I'm going to translate that, or attempt in this case, to translate it up to the graph. Notice that there's no graph above or below it. Because there's no graph above or below it, there's just anything that on that area is not defined. So it would just basically be does not exist, because the graph literally does not exist over there. It's not defined for anything greater than 4. Does that help? Perfect. Any other questions? All right, so 5 right here is a little bit of a tricky question right here. Let's read through it. If you know that the limit as x approaches c of f of x exists, so you know that this exists, can you find its value by calculating the limit from the right? Give reasons for your answers. Let's start with this. Yes or no? Think about that for a moment. Turn to your neighbor and ask them yes or no. And what do you think? And go ahead and discuss for a moment. Let me give you a minute to discuss yes or no, and then why.
Right, because it could be around 20.
All right, let's come back together. I heard Griffin right up here with some confidence. I think we're right. Listen, no pressure on him, right? Let me see what the general consensus is. How many say yes? How many say no? All right, so it looks like the no's carry. Griffin, it sounds like you had an idea. What was your idea? Just kind of talk through it for a moment.
Oh, well, like it could be like a split, like line thing, like one could be on the bottom and one could be on the top. And if they're coming from the right one way, it could be a different point when you're coming from the left.
Okay, so you're thinking something like that first example we had right here, like this. All right, so, I mean, this is a graph, but let's see. Let's see if this first condition holds. Is that, so this fails. So that's not the example. Well, I will go ahead and say the majority of you who said no, that was the correct answer. You can't necessarily figure it out. So let's think of, so this is maybe, this is a thought process, but it's not quite the example we're looking for. So if you know that this exists right here, can you find its value by calculating the limit from the right? Anyone see an example that were Emma?
So this might be wrong, but technically you can't because it could be like you calculate it from the right and it does not exist. But you know it does exist, so it's going to be the value from the left. So whatever that value is, so it might not necessarily come from.
Very good. That is the idea. It's exactly this example right here. You can see that we have the limit that exists. We know it's from the left, but we don't know it from the right. So that's exactly the example that we're looking at here. So this one's a little bit tricky because it all comes down to the domain. So if I did say, if you know that the limit exists and like the domain is negative infinity to infinity, if I said the domain was all real numbers, then the answer would be yes, because you wouldn't have any boundary points to worry about. And I think that's what you were trying to kind of get your mind around, is like, what would happen? So the answer to this question is not necessarily, let me change back to blue because I like blue, it's my favorite color. Not necessarily, wow, I'm not sure what I'm spelling here. Necessarily, C for M through O. But I will say the answer is yes if the domain was all real numbers. So a little bit of a tricky question, or I'll say yes if, I'll say domain, yes if C is not I'll just say it this way. If C is I'll make up my mind eventually. Give me a sec, interior point. So yes, if C is an interior point, then you would be able to go ahead and just figure out that limit right there by considering the value from the right. So fun little question right there, making sure you really have that little kind of corner case in your mind. Does anyone have any questions on that example? Very good. Glad to hear everyone discussing that. Chapter 2, not very hard computationally, but conceptually there are a few tricky things that you want to make sure you give your mind time to wrap around. So, okay, then let's look at the absolute value one right here. See how one-sided limits could help us out algebraically. So you can see there's this same function right here that we looked at the first page. And the thing that we tried is, of course, we tried putting it in 0 over 0. But let me remind you, the absolute value of x, it is a piecewise function that is negative x when x is less than 0, and it is x itself when x is greater than or equal to 0. So I'm going to go a little bit out of order. I'm going to make a 6b here and consider the limit as x approaches 0 from the left of x over the absolute value of x. I think it's a little easier to see it from the left. So remember, when we say x we're approaching x from the left-hand side, what type of numbers are we looking at? Positive or negative ones? Negative. So if we're looking at negatives, we're going to be at this top piece of this piecewise function. So what we can actually do, because we are given a one-sided limit, we can rewrite this as the limit as x approaches 0 from the left of x over negative x. I can get rid of the absolute value because I know the values of x are negative that I'm looking at and just replace it with the appropriate piece. That is only possible, though, when you're considering some information given to you about the domain. So that's a substitution. And then, of course, we could go ahead and can simplify this. The limit as x approaches 0 of the left of negative 1. Everyone see x divided by x leaves you with negative 1. What is the limit of a constant function? It is the constant. So what is the limit here? There's nothing to plug in, so it is just the constant function. So in the case of the 6 given, when we're looking at the limit as x approaches 0 from the right-hand side, we have x over, well, what should I replace the absolute value of x with? Just x. Which, of course, will then leave us with the limit as x approaches 0 from the left of 1, which, of course, is just 1. And we already actually figured that out graphically, but make sure you really grab this idea, because this will show up a lot more in chapter 3 when we're considering where certain derivatives, namely the inverse trig functions. That is the idea of when you have information about the domain, it allows you to get rid of the absolute value at certain times. Let me say that again. When you have certain information about the domain, it allows you to get rid of absolute values appropriately. Any questions on 6 or 6b? Then here's an example to think about right here. So notice that this scenario, the absolute value has been switched, and we're considering the limit as x approaches negative 2 from the left. First, try to plug it in. You get negative 2 plus 3 times 0 over 0. So that does not work. So what can we do? Well, take a moment and try it. How would you find the limit for 7? If we're showing all our steps, the first thing to observe would maybe be what I wrote here, is that because I'm approaching it from the left, notice again, this has been shifted 2 to the left. If you think about this plus 2, this is going to cause the graph to go left 2. So that moves the absolute value function's graph to the left. So you can now see that this is the piece that you would have. You would substitute the absolute value of x plus 2 with minus the quantity x plus 2. In doing so, you could then simplify. You'd find the limit as x approaches negative 2 from the left of x plus 3. And then you would simplify that second quotient there to just minus 1, because both the top and the bottom are just the same quantity with one negative. So when all is said and done here, the limit would have been minus 2 plus 3 times minus 1. Where does that work out to be? Minus 1? Awesome. So that is how you would use one-sided limits algebraically, most commonly when it comes with with absolute values. Any questions there? By the way, I don't know if this question is going to be on this semester's versions of the test. It has been on previous semester versions of the test, and it is one of the most commonly missed questions. I think just kind of that idea of most people are off by a sign because they'll cancel without it considering the sign. So be careful with that. I don't know, I haven't written this semester's version of the test yet. So just notice that problem just comes to me from previous semesters. Okay, the last thing we're going to do in this section is really not as much about one-sided limits. I can't remember why they put it in this chapter. I think it has to do with the actual proof of it. We're not going to prove this. We're going to just look at it algebraic or graphically and consider some other trick that we can use when it comes to trigonometric functions and limits. So this function right here, sine of theta divided by theta, about x, actually I should say about theta equal to 0 because we're talking about theta here. It doesn't matter whether it's just change of variable. Is important in the study of the instantaneous rate of change in trigonometric functions. So this instantaneous rate of change involving trigonometric functions, this right here is going to be section, if I recall correctly, 3.5. So we'll talk, so this what we're talking about on this page allows you to understand where everything comes from in section 3.5. So if you're really aiming to really understand like all the connections, this is something that you'll want to just kind of have in your back pocket for when we get there. And it's this little theorem about this limit. So right here we have the graph of sine of theta over theta. Notice this is kind of wavy. It's just that's kind of how trig functions work. They're periodic. Notice it's not defined at 0. There's a hole here because, again, you have a 0 in the denominator if you tried to plug in 0. And what we can do is we can graphically look at the answer to this right here. If we approach 0 from the left and we approach it from the right, what do we find is the limit of this function? We're pointing to that hole up there, which is at y equal to 1. So we can use this theorem or this kind of limit we just computed using the graph above to simplify more complicated expressions involving limits. But one thing I maybe want to call out, like what am I paying attention to? If you look at the denominator here, and if you look at the input to the sine function, notice that those are the same. So this identity, you could think about it as, or this concept of this limit has different forms as long as you have the input to the sine and the denominator matching. So let me put it this way. So these must match. And you get 0 over 0. We get that indeterminate form. When plugging in. All right, so this is going to have a little bit of a different flavor compared to the earlier part of this lesson, but we have a couple examples here using this identity. So if we look at number 8, what we could try to do is plug it in. So let's see what happens when you plug it in. You get sine of the square root of 2 times 0 over square root of 2 times 0, which is 0 over 0. By the way, just maybe here for reference, sine of 0 is equal to 0 because if you think about the unit circle, that's where we're at angle 0, and the y value at angle 0 is 0. So that doesn't work. But notice that the input to the sine and the denominator, they match. So we can just go ahead and say that this is equal to 1, and our reason being is because theorem 7. You don't need to remember that it's theorem 7 or whatever. You just want to recognize that pattern. The reason that works is because this square root of 2 is just a transformation. What type of transformation is that? Anyone think they know? It's a horizontal square root of 2. Stretch. Shrink. Because it's greater than 1. So it would be a horizontal shrink. So that's the idea, but be careful because you're going to start to grab onto this and see they're matching. And you're like, okay, these match. But what do you still always want to do first? Plug it in. What happens when I plug this in? I get sine of 5 plus 5 divided by 5 plus 5, which is sine of 10 over 10. And again, you may need to grab a calculator just to find the reference right there. This is not a nice angle, but make sure your calculator is in radians. So you can see over here on the left, I'm clicking radians, there we go. And if I did 10 and I found its sine, you would see it's approximately 0.5. And then if I divided that by 10, I would get approximately negative 0.05. So this right here is approximately negative 0.05. And maybe just for reference, again, if there's no degree symbol, remember that that is radians. So if you are doing any sort of computation with trigonometric functions, make sure it's radians. Just to make sure the idea clicks, 9b, what is the limit as x approaches negative 5 of sine of x plus 5 over x plus 5? Anyone think they know here? Volunteer? I heard it, was it?
1.
That is correct, it is 1. The answer here is equal to 1 because, again, technically you check. This is 0, this is 0, so ultimately this is 0 over 0, but because that condition holds, we can go ahead and use this idea up here. So that's the basic form of those problems. Does anyone have any questions on 8 or 9? And I feel like everyone gets nervous when I say that's the basic version because that usually means there's a non-basic version. So let's go over to the last page of this section and see what I mean by the non-basic ones. Take a look at number 10. First thing you always should try to do is plug it in. You sound a little less enthusiastic every time I ask that question, but that's okay. It'll help you remember it. So if I try plugging it in, I get sine of 2 times 0 over 5 times 0, which is 0 over 0. So plugging it in doesn't work. Nor do I have the matching input with the denominator. So what I have to do, I'm going to just go ahead and write it down here below. I'm going to rewrite the problem just to not clutter it. What do I need? I need a 2 down here instead of a 5, right? So remember, with fractions, you're allowed to move things around. What I can go ahead and do is consider the limit as x approaches 0 of sine of 2x over x, and I'm going to just slide this 5 over here. Again, remember when you multiply fractions, you multiply across the top and across the bottom. Everyone agree that is equivalent to what we started with? What did I say I needed in the bottom? A 2. I'll put it here, but if I divide by 2, I must also multiply by 2. So again, maybe the initial thought would be just be like, oh, multiply 2 over 2. But of course, then what you could go ahead and do is just write it, let's keep everything organized here, as, let's see. I'm going to go ahead and have sine of 2x, over 2 times x. And then I'll multiply this by 2 over 5. Does everyone see where that 2 over 2, where everything moved around? Now that we see that, remember the limit of the product is the product of the limits. So if you take the limit each part, take the limit of this part as x approaches 0, what do we get? It's what we've been working with. This one is the 1. So this right here is 1. And the limit of a constant is the constant. So what is the limit of 2/5? 2/5. So we ultimately end up with 2/5 right there. So any questions on that one? Let's go a little bit out of order. Let's go to 12. I see no signs. I feel like it should be a sin. Okay. But I do see the reciprocal and the quotient identities. So the first step here might be just to be like, okay, I'm going to rewrite this as the limit as t approaches 0 of tangent of t times secant of 2t times 1 over 3t. Just kind of move things apart. Gives me some flexibility. Anyone think, what do you guys think we would do now? Any ideas? Yeah, let's change these to sine and cosine. Let me give you a moment to try that. So again, remember that tangent is going to be sine of t over cosine of t. And then secant of 2t is going to change to 1 over cosine of 2t. Let me give you a moment with that in mind to see if you could go ahead and finish off this problem. So this may be one thing that you can do with your work right here. Does everyone see where I got this part? I've just rearranged the products so you can see that this t, I needed it over here with sine. I kicked this cosine out from the basement and said go over there. So that's why it's over here. It's just color. So this moved here. This came down. Let me change color. That came down. And then this 3 stayed here. So does everyone see how that is equivalent to what we had above? A lot of multiplication, just kind of moving fractions around. But we'll take the limit of each part. What is going to be the limit of the sine of t over t as t approaches 0? Not 0, it's going to be 1. 1 over cosine of, what is cosine of 0? Cosine of 0 is 1, so this is going to be 1 over 1. This is going to be 1 over 1 times 1/3. So what is the limit here? 1/3. Anyone get it? Well, that one's a little tough. And again, I didn't maybe give you as much time as you maybe need to process those the first time. But does anyone have any questions? All right, so let's call that a wrap for the lesson today. Have a good day, everyone. We are asked to find the limit of this right here. And of course, if I asked you the first thing you should always do when taking the limit, you're all going to say, yeah, you're really sounding less enthusiastic now. So of course, if you do plug this in, you will end up with a 0 over tangent of 0. And tangent of 0 is going to be 0 because remember that tangent of 0 is sine of 0 over cosine of 0, which is 0 over 1. So again, just a little bit of kind of a reminder of how the evaluation works with the trig. So if you can't plug it in, you need to find a way to simplify this. So if you recall from last time, the identity that we were working with, the property as the limit as t approaches 0 of sine of t, where the input of the sine function and the denominator match about 0, that is equal to 1. We found that graphically, and then we can use that as a shortcut to simplify some of these right here. So of course, we need to go ahead and get a sine. So we could go ahead and just rewrite this problem as the limit as t approaches 0 of 2t over sine of t divided by cosine of t. So again, you do now have a compound fraction right here. And remember, whenever you divide by a fraction, you multiply by the reciprocal. Very good, everyone. So what that will look like is that we will now still have the limit as t approaches 0, but we now have 2t times cosine of t in the numerator divided by sine of t. So one other thing that I'll also go ahead and mention about this identity or this property that we have above, that the reciprocal is also true. So if you were to go ahead and consider the limit as t approaches 0 of t over sine of t, this is also equal to 1. That simply follows from the limit laws. Essentially, you think about this as, you don't need to write this, but just to understand why that's true, you could think about this as 1 over 1, and then remember that the limit could be applied both to the top and bottom separately, and then just reciprocating both sides gives you that as well. So again, that statement is also true. So the reason I said that is because if you look at what we have this t time over sine of t. So that part will be what we have from above, and everything else is just there to kind of keep us interested in the problem, maybe to kind of maybe see how other functions are involved. So just using our limit laws, I'm going to rewrite this according to where I see that property from above. So we have t times sine of t, and then we still have 2 times cosine of t. And of course, you take the limit of each part independently. So this part is 1. The limit of 2 is 2 because it's the constant. And of course, you can just plug in 1 to cosine. Plug in 0 to cosine, which gives you 1. So again, there's the limit is gone at that point because I've used the limit to go ahead and get this red 1, to get the limit of a constant, and again, to consider the cosine of t as t approaches 0. So we ultimately just get 2 here. So again, that problem illustrated this idea up here that you could still reciprocate and you'll be fine to work with that property. Does anyone have any questions on what happened on number 11? Just kind of one other little thing to have in your back pocket. Great. The other one we'll look at is down here below. Hopefully you've kind of seen the pattern right here. Separate your trigonometric functions based off of their reciprocal and quotient identities. Go ahead and give this one a try to get yourself warmed up. While you do that, I'm going to take attendance, and then of course I'll go over it and see if there's any questions. So go ahead and try 13 to try while I just check on who's here. All right. Haley, Jill, Luke, Emma, Raul, Chapel, Destiny, Haley, Sarah, Cadence, Weston, Grace, Josie, Alfred, Savannah, Griffin, Say, Emma, Sarah, Christina, Rena. Oh, it's tomorrow, right? It's tomorrow, right? Okay. David, Roxana, Corbin, James. you're having some trouble, I went ahead and put up the answer on the screen, kind of color coded it. The trick on this one is essentially to go ahead and just use this 6x squared, which you already have over here, and then just put it over the pieces that you need it. So you have this sign, you have the sign of the 2x and the sign of the x there. So you can see that the green x went here, and then there's another green x right there. So there's where my x squared went. 6, I separated the 2 and the 3 because I need this 2x over sine of 2x there. And then it's a pretty straightforward computation once you've kind of set everything up based off of that property that we've looked at already. So there's the work for 13.